9.1 of the textbook, and also the introduction to Chapter 9. So before we get started, it's probably worth asking, what is an antenna anyway? We've learned in our section on time-dependent electric and magnetic fields that all oscillating electric and magnetic fields propagate. They essentially create the other version of themselves. Current creates a magnetic field, which if it's oscillating will create an electric field, and in turn a magnetic field, and so on. And so at some level, all circuits that create AC electric fields and currents are going to radiate. And by radiate we mean create fields that couple energy away from the circuit and into space. It turns out antennas are just devices that we use to optimize and control, or to engineer, the emitted radiation so that you can couple the electrical energy from a circuit to free space and back again in the way you want to. And antenna design is well beyond the scope of this lecture. But there are a couple things you might want to design into an antenna, or design into a system designed to couple electric energy out of a circuit, and into a propagating wave in space. One of these is basically how strong the field that you emit or radiate is in different directions. Maybe you want some spatial dependence, like a narrow beam, or you want it to go in all directions. You want the total power radiated compared to the driving power to be high. You want to design a circuit where most of the energy you pump in actually goes to create a wave of some type that propagates through space. We remember from transmission lines that in order to match a driving circuit to a load, we have to match the impedance. We also want to know basically the amount of radiation we get as a function of frequency, or the bandwidth of the antenna we define. And it may be that for certain high power applications we need to know the voltage or current spatial distribution on the antenna, because if we're really trying to pump a lot of power out to transmit a long distance, maybe you'd get some heat down or dielectric breakdown of the air if the fields get too high. So this is some of the things that we need to sort of understand as we start to begin to look into antennas. And I'll go ahead and say that there are two general classifications of antennas. Antennas that basically create distributions of currents that radiate, and what we call aperture antennas, where we create a particular electric or magnetic field distribution across some region in space, or an aperture, and then that has the radiating characteristics we want. And we're not going to be talking about aperture antennas. That's a more advanced subject. We're simply going to stick with the current antennas and some fairly simple ones. So let's go ahead and look at a diagram we've seen several times before, and so we're going to bring it back to you, since hopefully you understand this by now, where we had some kind of large sheet that supports a current. Before we had a DC source that was connected with a switch. Now we're going to use some kind of AC voltage source that drives the current in an oscillatory fashion, back and forth and back and forth. And we know from our previous experience we can look at the sheet of current either from the top view, where the current's essentially going to be going either down or up, or we can look at it from the side, where the current's either going to be going down or up, depending on the phase of the AC voltage. We know, because we've gone through this exercise at least twice before, that when the current's flowing down or into the screen in our top view, essentially what we're going to see is a magnetic field that, given the right-hand rule and Ampere's law, goes around in the clockwise direction. We know the magnetic field is going to propagate outward with some velocity that we know essentially is the phase velocity of the medium. We also know that the magnetic field drops off in strength as it goes away from our current source. And so essentially what we can do is we can put in our little paddle wheel using Maxwell's equations, where essentially we know the current of the magnetic field gives the time rate of change of the electric flux vector. This little paddle wheel, as you can see, is going to basically spin in the counterclockwise direction, which gives rise to an electric field pointing out of the screen at you. On the other side of the current sheet here, you're going to see the same thing. You're going to see a paddle wheel that spins in the counterclockwise direction. The electric field points right at you. So essentially you're going to see that the curl of the magnetic field creates a time-dependent electric field. And we've seen all of this before. These are propagating fields. If we go to a little bit later point in time and look instead of the top view at the side view, we still see our magnetic field, we see our electric field. We play exactly the same trick using a different one of Maxwell's equations, and essentially can see that we're going to see the paddle wheel spin clockwise and counterclockwise. This gives rise to a magnetic field that points in the opposite direction, and again I'm repeating myself. You've seen all of this before. And essentially what happens is that changing magnetic fields give rise to changing electric field. If we look at the side view on both of these, essentially what we're going to see is that when the current is flowing down, that's given by this cyan colored arrow right here, that we're going to get this field distribution. At some point later in time, maybe half a cycle of our AC voltage source, the current's going to be flowing in the opposite direction. It's going to be flowing up, and of course our fields are going to be flipped in direction. And so this really gives the sense that when we drive a current element with an AC voltage source, we get magnetic fields that flop back and forth. First they point in one direction, then they go through zero, then they point in the other direction, and of course this is going to give rise to our plane wave, which we spent a lot of time on, that essentially propagates with that phase velocity that determines on the properties of the medium that the wave is propagating. But as Arlo Guthrie said in Alice's Restaurant, this is not what I came to talk to you about today. What I came to talk to you about today was essentially how to use an antenna to create a current. So how do we go ahead and create this current? And now we have to go way back to Series 1 of these lectures on practical electromagnetics, back to our transmission lines, where essentially we have some AC voltage source. We call the generator over here. It has some intrinsic impedance. We essentially can drive a transmission line with impedance Z0, and we know that what we're going to see on that transmission line is that we're going to see essentially two waves, one going in this direction that we call the plus going wave, and one going in that direction, which we call the minus going wave. And the overall voltage on this transmission line is given by that expression right there, where it just basically describes a spatially varying wave on the transmission line, with amplitudes V0 plus for one direction and V0 minus in the other direction. The current, on the other hand, is a little bit more interesting. We simply get the current by dividing the voltage by the impedance. This is just Ohm's law, no surprises here. But the thing you note in the current expression, which is given in red, is instead of a plus sign, there's a minus sign, which means that the plus going wave and the minus going wave essentially have opposite directions. Not only are there two waves on the transmission line, or two current waves going in opposite directions, but the currents on the two conductors are themselves going in opposite directions. In other words, if the current on the top line is going in that direction, the current on the bottom line, which I've shown as the big red arrows there, is going in that direction. One way that we can understand this is to pull up our distributed circuit model of a transmission line. This should be bringing back some memories. And essentially, remember, we calculated the transmission line parameters by assuming a voltage across each of these sections with an input voltage there and an output voltage there. But we also talked about the current, and we had a current going this way on this part and a current going in that way on that part. So you can see that from our distributed circuit model, the currents are going to flow in opposite directions in each section of this transmission line. So why are we doing this review of basic transmission lines? How does this really help us? Well, the way we see this, essentially, is to think of our transmission line with basically our currents going in that direction and also in that direction, some voltage that we know is a function of the position on the line there, and thinking about attaching a load to it. The next thing we're going to do is we're going to take that load away. We're essentially going to take the load away and split the wires of the transmission line, essentially bend them so that instead of going straight, the current goes up in that direction. If we keep doing this and bend a little bit more and put a 90-degree bend in, you're going to see essentially we've taken our transmission line and essentially have had the current go in that direction and that direction. Of course, at some later point in time, when the phase shifts by pi, you're going to get currents that go down and down. What have we done here? Simply by taking a transmission line, pulling off the load, and bending two of the wires, or essentially driving two wires that are orthogonal, we see that we can create a current source where the currents are going to oscillate up and down, up and down, up and down. So let's take a look at this and see if we can understand this a little bit better. The first thing you're probably asking yourself, if you remember transmission lines at all, is to ask yourself, does any power get to this antenna that we've made? This driving this current that's going to radiate by bending our transmission line. And the reason that's a good question to ask is, remember, the reflection coefficient is given by essentially the difference between the load and the line impedance divided by the sum of the load and line impedance. We remember the reflection coefficient for a line that's open circuited, that essentially has nothing attached to the end. In other words, if we take this transmission line and essentially remove a load, as essentially we've done when we've basically stripped it off and turned those wires 90 degrees, that the reflection coefficient is 1, and that no power is going to be delivered. All the power is going to reflect back from the end of that transmission line and go back to the generator. So it's really a legitimate question to ask, that when we take this transmission line, remove the load, and simply bend the wires, if we don't just have the same thing as an open circuited transmission line with a reflection coefficient of 1 and no power being delivered. Now, if I'd given you this as a problem and basically done this, I would have counted the answer correct when we were studying transmission lines. But we know a little bit more now because we've studied electromagnetic fields, especially time-varying electromagnetic fields. And we know essentially that what's going to happen is that when we bend this transmission line, if we can make the case that some current flows here, even though the current at this point has to be 0 and the current at this point has to be 0, that if we get some sinusoidal or oscillating current, that some of the energy that's used to drive those electrons, that charge that goes up and down, is going to be radiated as electromagnetic radiation, which I've basically tried to illustrate as these lines of radiation leaving, essentially the blue arrows. This corresponds to a power loss, because we don't get something for nothing. If we take some of the energy that's coming out of this generator, drive it down to the end of our transmission line and can drive some kind of current, we lose some energy to radiation. One can think of this as a resistance or perhaps an impedance if there's a phase change, so that when we essentially put an antenna at the end of the transmission line, even though there's no load, because we're losing power to radiation, we at least have some type of thing that behaves like a load, that doesn't turn the energy into heat or turn it into mechanical motion, but takes the energy and radiates it out into space. So in fact, we do have this situation as shown here. If we drive with an AC source a transmission line and couple it to an antenna, that antenna acts like a load, but instead of turning the radiation to heat or mechanical motion or driving some kind of other circuit, it sends all that power out, if it's a good antenna, into space. And this idea of an antenna having an impedance and being a device that we put at the end of a transmission line that essentially turns AC voltage and current into propagating electromagnetic waves is exactly what we want to study when we start to learn about antennas. So that's a good place to stop for today. The next lecture will look at one particular type of antenna, a small dipole antenna, which is really about the simplest antenna we can